In 2.1, we're going to look at frequency distributions, and then we're going to look at different types of graphs involving frequency distributions. So let's begin by discussing what a frequency distribution is. Frequency distribution is a table, and it shows classes or intervals, and then the count associated with each of those. And we refer to the count as the frequency. So the frequency is just how many items fall into this category. So whatever this data represents, values from 1 to 5, there are 5 of those. Values from 6 to 10, there are 8 of those. There are 5 values between 21 and 25. In each of the classes, there is a lower class limit and an upper class limit. And notice that each value only belongs to one class. The first class goes from 1 to 5, the next one from 6 to 10. So if we look at the numbers 3, 7, 12, 4, 3 only belongs to this class, 7 only belongs to this class, 12 only belongs to this one, 4 only belongs into that one. So the class limits are set up so that each value can only fit into one category. Otherwise, the frequencies will include values that are replicated. When we add up the frequencies, that should sum up to the total number of data pieces that we have in our set. So the class width, that is just the distance from the lower limit of one class to the lower limit of the next class, or the upper limit from one class to the upper limit of the next class. Notice here, if you take 6 minus 1, that is 5, so the width of each class is 5. Notice the first class, 1 through 5. How many numbers are in that class? Well, there are 5. So taking the difference between two consecutive lower class limits or two consecutive upper class limits will tell us that class width. Now, you probably remember what range is. Range is the difference between the highest and lowest value. If you take the highest data value and the lowest data value and subtract them, that's what we mean by the range. So when we construct a frequency distribution, we have to determine how many classes do we need. Now, different books use different ways of determining this. Some books take the square root of n, where n is the sample size, how many pieces of data we have, and we use that as an approximation for how many classes we need. Sometimes our classes are based on certain characteristics, so that we may have lots and lots of data points, but we might still only break our data into 5 or 6 classes. When teachers talk about grade distributions, we often talk about how many people failed, how many people made a D, a C, a B, and an A. And other than an F, most letter grades come in increments of 10, like 90 to 100, 80 to 89, and so forth. So sometimes we have predefined classes, so we don't necessarily use this formula to determine how many classes, but that varies depending on our type of data, what our data represents. So usually we want between 5 and 20 classes. Most of the data sets that we're going to do are going to have towards the lower end of that. If you have too many classes, then it's going to be hard to pick up on any pattern. If you have 30, 40 classes, but you only have 80 or 90 pieces of data, then a lot of classes might only have one item in that class, so it may be hard to notice any patterns in our distribution. So we have to determine how many classes, then we have to figure out how wide our classes are going to be. The way we do that is we're going to figure out what is our range. Then we're going to take our range divided by the number of classes, and whatever we get for that number, we're going to generally round up to the nearest integer. Even if that divides out to be like 11.2, which normally rounds down, to make sure that we have a wide enough range to cover all of our data from smallest to largest, we're going to round that up. Think about if we rounded that down, then by the time we had gone through all of our classes, there's that much of each class that's unaccounted for. So there may be several pieces of data at the upper end that don't even fall into one of our categories. So we round up to make sure that it's plenty wide to take care of our entire range of data. So then we have to find our class limits. So sometimes we start with the lowest value. Depending on what that lowest value is and our class width, sometimes we might go slightly below our lowest value. For example, if our lowest value is 52, we might want to start at 50 as our lowest class boundary instead of 52. Just depends on our class width and our data, so forth. Once we find one of our values, then we can find the rest of the lower limits by taking the class width and adding to that. And from there, once we get all of our lower limits, then we can find our upper limits. Remember, we don't want any overlap between our classes. Often we will make a tabulation chart and we use tally marks as we go through each piece of data. We'll put a mark in the class that it goes with so that when we get through tallying, we can just count up, okay, there are 3 tally marks, so there are 3 that go in that class. There are 7 that go in the next class. So let's look at an example. Let's look at this piece of data, or this data set. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 pieces of data. And let's divide this into now let's determine our range. So our lowest data value is 61. Our highest data value is not 91, but 92. I'm sorry. I'll get the right value in a minute. It's actually 97. Yeah. So 97 is the highest, 61 is the low. So our range is 97 minus 61. So 36. So that's our range. If we want to know our class width, we take our range divided by the number of classes. 36 divided by 5, that's 7.2. So if we don't want a decimal value for our class width. So let's round up to the next largest integer. So that would be 8. So our lowest value is a 61. So we could legitimately use 61 as the lower limit of the first class, or let's just step down to 60. That is up to whoever is making the distribution. So if our class width is 8, then if this is our first class, then the second class will start at 8 more, so 68. The next class will begin at 8 more than that. The next class will begin at 8 more than that. And the last class will begin at 8 more than that. So that's the lower limit for each class. Now the upper limit, if the second class starts at 68, then the first class should end at 67. If the third class starts at 76, the second one should end at 75. Notice this difference, remember, is our class width, so we can add 8 to each of these, and that will give us our upper limit. For the intermediate ones, we can just do one less than the next lower limit, but how would that work for the last one? So add 8 to the upper limits, and that would get them. So let's take each of our pieces of data and put them into classes. So 61 falls in the first category. 83 falls into this category. 91, 89, 71, 62, 92, 81, 72, 89, 72, 64, 97, 77, 76, 64, 73, 84, 74, 81. So the first class has 4, the second has 5, 5, 4, and 2. So those are our frequencies. So this is a frequency distribution. It tells how our data is distributed, hence a distribution, among the different categories. Now, occasionally, we like to know the midpoint of a particular class. So anytime you want a midpoint of anything, you take the low value plus the high value and divide by 2. It's basically the average of the highest and lowest values. So if we want the midpoint, let me see. Let's erase a little bit here. And I'm going to extend this to the left. If we want the midpoint of that first class, we add those to the low value. That's 127. 127 divided by 2, or 63.5. For the next one, add those together, divide by 2. We add them together, what's that, 143. When we divide by 2, we get 71.5. Notice there's a difference of 8 between these. If our class width is 8, then from one midpoint to the next, that's also a distance of 8. So if we add 8 to here, our next class midpoint is 79.5, then 87.5, then 93.5. So those are the midpoints for each of our classes. Sometimes when we display our frequency distributions, sometimes instead of displaying the class boundaries or the limits for the class, we'll display the midpoints. Another thing we often calculate is not just the frequency, but the relative frequency. It helps put in perspective as a comparison to the whole sample, how many fall into each category. So instead of just the count, instead of just the frequency in that category, then how is that as compared to the whole thing? Is it 5%? Is it 70%? So let's copy. Let's copy this. Over. So here's the same data. Let's cut this for now. Let's look at what our relative frequency would be. So we counted earlier and said we have 20 pieces of data. So in the first class, there are 4 of the 20 pieces in that first category. Of course, that reduces to 1/5. 1/5 as a decimal is 0.2 or 0.20, 20%. The next category has 5 pieces of data out of the 20, which is 1/4 or 0.25. The next one has 5 out of 20 pieces. So the relative frequency there is 0.25. 4 out of 20 is back to 0.20. And then for the last class, we have 2 out of 20, which is 1/10 or 0.10. So if you want to think about these as percentages, the first category has 20%, then 25%, 25%, 20%, and 10%. So those are what are known as relative frequencies. Something else that we often are interested in are cumulative frequencies. So the cumulative frequency, cumulative means the total, and that is starting from the bottom. So if we start at 60, by the time we have made it through the first class, we have 40 pieces or 4 pieces of data. When we have gotten through the second group, we have the 4 in the first group, and now we have 5 more. So we have accumulated 9 pieces of data by the time we have made it through 2 classes. Now for 3 classes, so my numbers got chopped off over here when we copied and moved things around. But when we get through the third category, we have the 9 that we already have from the first 2 classes, and then we've gotten 5 more. By the time we have made it through the 4th category, the fourth class, we have the 14 previous values, and now we have 4 more. And then when we have gotten all the way through the last category, we have the 18 previous data values. This last category or last class has 2 pieces of data, so we have a total of 20. So these are our cumulative frequencies. From this distribution, we can notice several things. We can notice that not many people fell into this last category. We can also notice that by the time we get through the first 3 categories, that is a large majority of our data. Most people, let's let these numbers be test scores for a particular class, most people, 14 out of 20, had test scores that fell into one of these first three categories. On the other hand, if 14 fell in the first three, then that left 6 that were in the top two categories. So only 6 out of 20 people made between 84 and 100. So these distributions help us have a better understanding of the patterns and the way our data is spread out. Let us draw conclusions about our data. So now that we have actually made some frequency distributions, let's look at making some graphs. The most common graph for a frequency distribution is a histogram. A histogram is just a bar graph where in the horizontal scale, it tells our data values. In the vertical scale, it tells frequency. Now that could be actual frequency, or it could be relative frequency. In some cases, there are even cumulative frequencies. One important thing to note is that the bars have to touch. If the bars aren't touching, that gives the appearance that there are gaps between our classes. We don't want that. We don't want any misunderstanding when people look at our graph. If bars touch here, but they didn't touch somewhere else, that would give the indication that there's a section of values for which there is no data, where nobody fell into that category. So before we make our histograms, we need to determine, well, what are the boundaries going to be for our bars? And this can kind of be a little confusing, and different books handle this different ways. Okay, so since we do not need a gap between our boundaries, notice this statement. The numbers that separate classes without forming gaps in between them, I got distracted by something. We can't use class limits for our boundaries. We actually have things called class boundaries. What we mean by that is, notice if we look back to our classes, the first class goes from 60 to 67. The next one starts at 68. Notice there's a gap between 67 and 68. Now, some people only grade tests on integer values, which means you can only make things like 83, 84, 85. I actually grade usually to the half of point. So it is possible in my classes to get a 67.5. So there is a gap in between here. So the way we handle that is we create what's called a class boundary. And again, different textbooks handle this a little bit differently. But the way this book handles it is they take the difference from the lower or the upper limit from one class to the lower limit of the next, which on these, the difference from the upper limit to the next lower limit is 1. And they cut that in half. So 0.5. So to make the boundaries, let's just put them here. For the bottom class, we will add a half a unit to the upper limit. And technically, we're supposed to take a half from the lower unit. So that would go down to 59.5. For the next one, we would take a half away from the lower limit. So 68 go down a half. That would get us to 67.5. For the upper one, we would go up 0.5. For the next one, go down 0.5 at the bottom. For the top one, go up 0.5. And we would do that for each of these. Notice our class width here is 8. In this class, it could be a 60, a 61, a 62, a 63, a 64, a 65, a 66, or a 67. 8 different items could fall into this class. Well, what's the difference between 67.5 and 59.5? 8, if you subtract those. Also notice there are no gaps between our successive classes. So that's the difference between these are class limits, but these are class boundaries. Now, technically, for our set of data, there are no 67.5, 75.5s. So everything that's in between here goes into this category. Everything between here goes into this. In between here goes into this. But since there are no data values at the edges, nothing gets replicated. Some other books use a less than or equal to and a less than system where basically they say in a category, we're going to, if it's a 60, it falls into the top, into this category, but if it's on the upper limit, it doesn't fall into that category. And it gets really, really confusing when you do it that way. So this is just a different system to come up with boundaries, but these are the actual data values that fall into those categories without having to remember which edge gets included. Do we include it in the lower edge or the upper edge? They have another example here. They did the same thing. We have some classes. From one class, the upper limit to the lower limit of the next class is a distance of 1. So half of that is 0.5. So they take 0.5 away from the bottom end and add 0.5 to the upper end. And they do that for each one. Now they took that and they put that into a histogram. Let's actually put ours into a histogram. Let me see. Let's add a page. And so our lowest class boundary is 59.5. And we have, remember we have 5 classes. So this is the first, second, third, fourth, and fifth. So let's see, go the right way. So the first one goes to 67.5. The next one goes to 75.5. The next one goes to 83.5. Then 91.5. Then 100.5. Not 101, but 100.5. Did I say that right? So 659, 67, 0.5, 75, 83, 91, 100. Okay. So the first category contains 4. So 1, 2, 3, 4. So this first bar is going to go up to 4. The next category has a total of 5. So our bar for the next category needs to go up to 5. Then 5 again. Then 4 again. And then remember our last category only had 2. Now a histogram is going to have a title. So on our title, it might be 20 exam scores. These are the scores, and these are the frequencies. So this is 1, 2, 3, 4, and 5. So just by looking at the graph, it gives us a visual of how the data is distributed, how many fall into each category, and so forth. Some graphs will have the relative frequencies on one side, the actual frequencies on the other. Sometimes we replace the frequencies with the relative frequencies, but one thing to note is the histogram is going to look identical. The only difference is going to be the vertical scale. So remember, for our first bar, if we go back to the relative frequency, we deleted that. That was 4 out of 20. That was 20%, or 0.20. These were 5 out of 20, or 25%, 0.25. So this would be like 0.05, 0.10, 0.15. These are just the relative frequencies. So if we looked at the graph, we could quickly see this top category, only 10% of the people fell into that category. For this category, 20% of the people fell into this category, and so forth. Another construction is a frequency polygon. And a frequency polygon is just a line graph where we have points basically at the peak of each bar. At the peak of each bar. Kind of different ways we could do this, but if we draw our horizontal and vertical scale, our boundaries let's copy these boundaries. Paste them in. And put our scale back over here. So after we had gotten through the first category, and if I remember this correctly, often they put it actually at the midpoint instead of the edge, but we can do it either way. We'll do it at the midpoint. When we, in the first category, it has a frequency of 1, 2, 3, 4. The next category had a frequency of 5. The next frequency had a total of 5. The next category had 4. The last one had 2. We always begin at 0 and end at 0 for our frequency polygon. So lower than 59.5, there is 0 data. And then when we have gotten through this first category, we've gotten up to 4. And in the next category, we go up to 5. In the next category, we're still at 5. And then our frequencies start declining until when we get above 100, there are again none that fall into that category. So it's just a different visual representation to tell you the trend of the data. We can see none of our data lies lower than those values and kind of where the majority of the data is. So that's what we call a frequency polygon. Let's see. An ogive, it deals with cumulative frequencies. Again, the horizontal scale lists the upper class boundary for each class, and the vertical scale is the cumulative frequencies, and we have a point at the upper class boundary and the cumulative and the corresponding cumulative frequency. So, as an example, here are some upper class boundaries for some data. These are the frequencies for each of their classes, and these are their cumulative frequencies. So the corresponding ogive will look like this. Notice before 190.5, when we get below that category, there's none. There's no data. And then when we get through the first category, we've gotten up to 3 values. By the time we get through the second category, we'll have gotten up to 5. So by the time the second category is over with, we've gotten up to 5. Then we've gotten up to 10 by the time we get through the next category, and so forth. One advantage to the ogive is it lets us see when we have the greatest increase from one step to the next. We might see that, hey, there's a more of an increase from here to here than there is from here to here. So it often helps us quickly compare corresponding values. So that is an ogive.